In this video, we're going to go through oxidation reduction reactions, aka redox reactions. So in a redox reaction, electrons are being transferred. One substance is losing electrons, and that substance is being oxidized. The other substance gains electrons, and that substance is being reduced. Now, I know that sounds a little backwards, like how can I be reducing when I'm gaining something, but that's just how it goes. There's an easy way to remember this, and it is Leo, the lion, says grr. So loss of electrons is oxidized, Leo. Gain of electrons is reduced. Now there are other ways of remembering this, but that's the way that I like to remember it. So feel free to figure out another mnemonic, but Leo the lion says grr is my favorite. All right, so here's an example. It says a piece of iron is immersed in a solution of copper 2 sulfate. Now, if you look at our numbers here, copper 2 sulfate goes from having a +2 charge to having no charge at all. So to go from a positive charge to no charge, you would have to gain electrons. And if you're gaining electrons, we go back to Leon the lion says grr, gain of electrons is reduced. Now, iron goes from 0 charge to a +2 charge. To go from 0 to +2, you would be losing electrons. And again, loss of electrons is oxidized. So that's what's happening in this reaction right here. Now, oxidation numbers. There are a bunch of rules that you need to know. The first one, for an atom in its elemental form, its oxidation number is 0. So when you see that it's being written as just magnesium or iron or hydrogen, oxygen, chlorine, oxygen, etc., its oxidation number is 0. For a monatomic ion, its oxidation number is equal to its charge. So if you have something that's an ion that's by itself, like a magnesium ion or a chlorine ion, it's going to be equal to its charge. So +2 - 1. So if you go back up and look at the example that we just did, those were all ions. I had a copper ion and I had an iron ion right here. So whatever the charge of the ion is equal to its oxidation number. The oxidation number for oxygen in a molecular compound is always -2. So in this example where we have H2O, oxidation number for oxygen is going to be -2. The exceptions are peroxides, where oxygen will have an oxidation number of -1. All right. Now, there are some rules that we follow to determine oxidation numbers. So again, these are kind of like the standard set of rules right here, but sometimes you run into situations where there isn't a rule for it. So how do you determine the oxidation number? When you have hydrogen, hydrogen is +1 when it's bonded to a nonmetal. So in the example of hydrochloric acid, HCl, chlorine is a nonmetal. Hydrogen, in this case, is going to have an oxidation number of +1. When it's bonded to a metal, when it takes the form of an anion, so in this case, magnesium is our cation, and then hydrogen is our anion, it's going to have an oxidation number of -1. Okay, so depending on what it's bonded to. For other covalent compounds that do not contain hydrogen or oxygen, the most electronegative element has an oxidation number equal to its charge as an ion. So in the example of BF3, the oxidation number for fluorine is going to be -1. So if you were to look up fluorine's charge, fluorine is -1, and that's where the oxidation number is coming from. So between boron and fluorine, fluorine is more electronegative, and that's why we're using the charge as an ion as the oxidation number. In the case of phosphorus pentachloride, the oxidation number for chlorine is going to be -1 because chlorine's charge as an ion is -1. between phosphorus and chlorine, chlorine is more electronegative. So we're going to use chlorine's charge as an ion as its oxidation number. Okay, remember electronegativity is larger as you head to the upper right-hand corner of the periodic table. Okay, here are some other ones. So the sum of the oxidation numbers for all of the atoms in a compound must equal the overall charge of that compound. Okay, so in this example, ClO3, the charge is -1. We know that oxygen's oxidation number is always going to be -2, and there are 3 of them, so that's where we're getting -6 here. So if the overall compound is -1, we know that oxygen's charge is -6. We're solving for X here. So since there's 1 chlorine, the oxidation number must be +5. And that's where that's coming from. All right, we already did this one, but let's go through and let's do it anyway. So it says find the oxidation numbers in phosphorus pentachloride. So chlorine is the most electronegative. So chlorine's oxidation number is going to be -1. Phosphorus, we have to look at the overall charge of the compound. So there is no charge here. So whatever phosphorus's oxidation number is, and then we have 5 chlorines. Each chlorine is -1, and that is going to sum up to 0. So what -5 equals 0? Well, phosphorus is going to have to be +5 to make this work. So again, to determine what's being oxidized and what's being reduced, we have to look at oxidation numbers. So in the first example that we looked at with the ions, it was really easy. We were just looking at the charges. But here, we have to look at oxidation numbers. Okay, so oxygen is in its elemental form. Its oxidation number is 0. Calcium is in its elemental form. Its oxidation number is 0. In our compound, where we have calcium and oxygen, oxygen, we know, is always going to be -2. There is not a charge on our compound here, so I know that calcium plus oxygen is going to be 0. So the only number that makes this work here is +2. So that's where this oxidation number is coming from. So calcium goes from an oxidation number of 0 to +2. So in order to go from 0 to +2, you would have to lose electrons. And again, Leo, the lion, says grr. Loss of electrons is oxidized. So in this case, calcium is being oxidized. Oxygen is going from an oxidation number of 0 to -2. In order to go from 0 to -2, you would have to gain electrons. And again, gain of electrons is reduced. Okay, here's another example, and this one's kind of nasty. We got a lot going on here. So let's pick this apart. So we know that oxygen's number is -2. Okay, so because oxygen's number is -2 and there are 3 of them, that means the total here is -6. Okay, now here's where it gets a little tricky because we got a lot going on here. So if I take my ClO3, this is a polyatomic ion and it has a charge of -1. So if we split this up, we know that our oxygen, our total negative from oxygen, is going to be -6. Our oxidation number from those 3 is going to be -6. So what plus -6 gives you -1? Because that's the overall charge for our ion here. Well, it's +5. So that's where the 5 is coming from here. So if you have a polyatomic ion, you have to look at the charges to kind of determine the other pieces. Okay. Now, going back to our compound here, we know that there is no net charge here. No net charge. So since this piece right here was -1, our potassium has to be +1. Okay, in our next piece, we have NO2, which is a ion. Okay, so NO2 has a charge of -1. So oxygen is -2, and there are 2 of them. So let me rewrite this, NO2. There are 2 of them, so that would be -2 and -2, which is -4. And we don't know what this is, we don't know what the nitrogen is, but then the whole thing has to be -1. So nitrogen has to be +3 to make that work. +3 -4 gives you -1. Okay, and then since we don't have a net charge on our compound here, we know that this piece right here, this -1, and then whatever hydrogen is, has to equal 0. So the only thing that makes sense, if this is +1, this has to be -1. So if you have more than 2 things in a compound, one of the components is probably going to be polyatomic. So that's where you have to look at those charges. Now, the next one is a little bit easier because we only have 2 things. Okay, we have potassium and chlorine. So here we have to look at electronegativity. Chlorine is more electronegative than potassium, so we're going to go with chlorine's charge, which is -1. And then because there is no charge on the compound, we have to make sure that the 2 pieces cancel out. So that means that potassium has to be +1 to cancel out. All right, in the last one, we have NO3. Okay, this is a polyatomic piece right here, -1. So we have nitrogen and we have oxygen. We know that oxidation number for oxygen is always -2, and there are 3 of them. So the total here will be -6. And if the charge has to be -1 when we put those 2 pieces together, what plus -6 gives you -1? Well, that's +5. So going back to the NO3, which has a -1 charge, there's no net charge for the entire thing here. Hydrogen has to be +1 to cancel out with the -1 to make that work. Okay, so oxidation numbers are a little tricky. There's a lot going on. There's a lot of rules. This is just kind of a crash course in oxidation numbers. But let's take a look at what happened here. We're going to look at each individual piece. Let's start with potassium. Potassium goes from +1 to +1. No change here. Okay, so nothing happens. Chlorine goes from +5 to -1. So here you would be gaining electrons. Okay, and I'm going to write it out again. Leo the lion says grr. So we gained electrons. Gain of electrons is reduced. So chlorine is being reduced here. Oxygen goes from -2 to -2. Nothing happened. Okay. Let's see. Hydrogen goes from +1 to +1. Nothing happened. Okay, so then finally we have nitrogen. Nitrogen goes from +3 to +5. So here we would have to lose electrons to gain a larger positive charge. So if we lose electrons, we are oxidizing. And that, in a nutshell, is how a redox reaction works. If your brain hurts right now, that's normal.